Hello, hello. Okay, so good evening. Welcome to the live session number 7, this NPTEL course, Waste to Energy Conversion. My name is Devarun Banerjee. I'm a PhD PMRF scholar of Indian Institute of Technology, Delhi. In this week's lecture, the initial lecture was about fermentation, basically the last part of fermentation, microorganisms, and product recovery for production of ethanol from lignocellulosic biomass. This is the spelling is wrong. It will be lignocellulosic. And then ethanol production via the gasification route and butanol production from lignocellulosic biomass. So if you see the fermentation technique, uh, glucose from glucose, 2 moles of ethanol is formed and 2 moles of CO2 is formed. And also apart from that, other reactions from xylose also or arabinose also, ethanol can be formed. So these reactions are there. Xylose, arabinose, these are pentose, like 5 carbon sugars. And the ethanol yield can be calculated via this formula. Uh, mm, it's a multiplication of ethanol concentration and initial volume of liquid medium and divided by mass of the substrate, Cv divided by m. Ethanol yield can be calculated by this formula. Uh, Among the different other reactions, you can see the cellobiose or xylobiose, 10 carbon sugar, and from them ethanol can be formed via hydrolysis reaction. Ethanol productivity is defined as the amount of ethanol produced per unit of substrate utilized per unit of time. And if you see the formula again, so the ethanol productivity will be Cv divided by m into T. T is the time. Rest of the things are same as the ethanol yield. That is why it is written as correlated with the ethanol yield divided by time. And for if you want to denote it in terms of milligrams, that's why the thousand is multiplied. And then the maximum theoretical ethanol yield is the ethanol produced in reactor divided by initial sugar in reactor into 0.511 into 100. Uh, the different microorganisms, if you see for fermentation for lignocellulosic biomass, the sugar for starch-based ethanol production is mostly hexose sugar or glucose. However, for lignocellulosic biomass, mixed pentose and hexose sugars are available. So they are, as already earlier showed, that there are hexose, pentose sugars and also other 10 carbon sugars and 12 carbon sugars. Those are also available for ethanol production. The overall general idea would be same by hydrolysis, and it will be producing ethanol and CO2. The most common and traditional microorganism for fermenting sugars into ethanol is a yeast, which is named as Saccharomyces cerevisiae. However, the natural strains of this yeast can ferment only 6-carbon sugar and hardly pentoses. So this is the issue. This particular strain. So therefore, some yeast strains such as Pichia stipitis, Candida stihati, Candida parapsilosis can ferment xylose, but not efficient for hexose fermentation. So there's the differentiation comes. If you want to ferment pentose like xylose, you want to go for this kind of yeast strain, or if you want to ferment this hexose like glucose, you want to go for Saccharomyces cerevisiae. So basic product recovery side, if you see for ethanol production, uh, there are basically majorly two sides. One is the thermal route, another one is the low temperature route. The low temperature product recovery route are basically via membranes and molecular sieve water adsorption. This kind of separation techniques are used for the product recovery to separate out the desired product, which is ethanol, from the solid residue wastewater. And via thermal route also, it can be done, such as SIMS and where the steam stripper, distillation tower, this kind of unit operations are there. The first process that was used in many of the earlier ethanol plants is the so-called azeotropic distillation or ternary distillation process. It consists of introducing a third component, which is benzene or cyclohexane, to the azeotropic solution, which forms a heterogeneous azeotropic mixture. So, what is the benefit of this azeotropic mixture? When this mixture is distilled, the anhydrous ethanol is produced at the bottom of the distillation column. Okay, so if you see the boiling point of different components, ethanol boiling point is very similar to the mixture boiling point, right? But when there is the cyclohexane boiling point is about 80 degrees Celsius, but this particular mixture of cyclohexane and water, this mixture boiling point is much lower. Apart from that, another early method is called the extractive distillation, which consists of adding a ternary component that increases the relative volatility of ethanol. Here, the anhydrous alcohol is produced and withdrawn at the top of the distillation column. Apart from this particular fermentation technique, there is another also technique, which is the gasification technique. So, so by direct gasification, basically the primary product is the syngas. So from syngas, the biological reactions such as fermentation, we form the ethanol. Also, there is the thermochemical catalytic route, which can also form ethanol via from syngas as a feed. Okay, so nowadays, if you see the CO2 to ethanol, CO2 to methanol, this kind of research areas are getting very much uh, favored. So the CO2 is in an industrial point of view. Directly CO2 is not very much uh, directly available. Apart from that, there is also another important feedstock for ethanol. It will be the syngas. So using syngas as a feedstock to produce this kind of high value fuel like ethanol can be a major boost up. Apart from the ethanol, another important product which can be also obtained is the butanol. Butanol is a major co-product of acetone, butanol, and ethanol fermentation. As the typical proportions of acetone, butanol, and ethanol are 3 is to 6 is to 1. You see the major maximum component is the butanol. So that is there comes also the challenge to uh, maintain the selectivity or yield of the relative selectivities and yields of the different components. like towards ethanol, or the reaction to move towards the butanol. There comes also this kind of challenge. Okay, there are these further detailing of this kind of butanol producing biological route is discussed here. And again, similarly, the butanol recovery, the partial solubility of butanol in water creates impediments in its downstream processing and extraction from the fermentation broth. The high energy requirements subsequently add to the process expenditures, making the overall butanol production expensive. Uh, to make the AB, this acetone butanol ethanol fermentation profitable, many in situ product recovery systems have been developed, a few of which include adsorption, liquid-liquid extraction, power evaporation, gas stripping, and supercritical fluid extraction. The research on these butanol recovery techniques are still at infancy stage, and none of these technologies have been implemented at the commercial level. The representation of butanol recovery by adsorption. So further into the butanol recovery part, the adsorption of butanol onto a packed column from the dilute solution or fermentation broth, followed by desorption by heat treatment or displacer. And also the activated carbon, zeolite, polymeric resins, silica light, adsorbent resins, amber light, polyvinyl pyridine are thoroughly studied for butanol recovery. The first question of today's is the maximum theoretical yield of ethanol can be calculated as. These are the four options. Correct answer is Y max equals to ethanol produced in reactor in gram by initial sugar in reactor into 0.511. Biological route uses dash bacteria for the production of ethanol from lignocellulosic biomass. Pichias typitis, Clostridium jungdali, Candida parapsilosis, Lactobacillus. Correct answer is Clostridium jungdali. In a high-rate biogas plant, food waste is anaerobically digested to produce biogas. The slurry contains 8% of solid food grains. No one has joined. One person joined and left. The elemental composition of the food grains on dry basis is carbon 58%, hydrogen 8%, oxygen 26%, in nitrogen 8% mass basis. Around 80% of the food grains are converted to sugars, are converted to biogas, and all the hydrogen forms methane. If the flow rate of the slurry is 4,500 liter per day, calculate the rate of biogas CO2 plus methane production. Flow rate of the slurry. So it's given as 4500 liter. Dry solid food grain used is 8%, so 360 kg. And take a and density of slurry assuming at 1 kg per liter. So simple, based on the composition, carbon, hydrogen, oxygen, nitrogen present in the dry food grain get in the kg terms. Then 80% of the food grains are converted to biogas. So we take each and every component. So carbon converted to biogas. Originally it was 208.8 kg. 80% converted to biogas. So 80% of 208.8 kg. Similarly, so the methane production will be total molecular weight 6. 4 is the molecular total hydrogen weight. So total is hydrogen converted to biogas 23 kg. So it will be 92.16 kg. Now carbon used for methane production is this 69.12 kg. Carbon used for CO2 production, the rest. So 167 minus what is used for methane, 167 minus 69, 97.92. So CO2 produced. This is the carbon we are getting. So 97 kg carbon is there in CO2. So just take the total. So 44 is the CO2 molecular weight. So 359.04 kg is the CO2. So methane we got earlier in the similar way. CO2 we got just total. So the rate of biogas production CO2 plus methane. This is a very important question. You must check and must practice for your examination. Another numerical question. During pretreatment, 50% of the mass of lignocellulosic biomass waste is converted to monosaccharides and disaccharides in the mass ratio of 6:4. The monosaccharides produce 510 gram ethanol per kg of monosaccharides, while the disaccharides produce 540 gram of ethanol per kg of disaccharide. Assuming same molar ratio of both monosaccharides as well as disaccharides as 1:1 in the respective saccharide types, calculate the ethanol yield. If you take the basis as 100 kg of lignocellulosic biomass, so monosaccharide and disaccharides produced 50 kg because they're taking the 1:1. So mass ratio is 6:4. Yeah. So it is given 50% of mass of lignocellulose biomass is converted to monosaccharide and disaccharides. It means that 50 kg will be monosaccharide and disaccharide. Among them, there is 6:4 ratio. So 50 kg divided into 6:4 ratio, so 30 kg monosaccharide and 20 kg disaccharides. Now, 1 kg of monosaccharide produces 0.510 kg of ethanol given, and for disaccharide is also given. So how much will be 30 kg and 20 kg producing ethanol? So total ethanol produced we are getting 26.1 kg. So ethanol yield with respect to total sugar, it is 26.1 divided by 550. The total sugar monosaccharide and disaccharide is 50 kg. So this 26.1 kg is coming from 50 kg of these mono and disaccharides. So per kg of mono and disaccharides, we are getting 0.522 kg of ethanol. And if we take the entire lignocellulosic biomass, so we are getting originally 100 kg of lignocellulosic biomass. So 26.1 by 100, so 0.261 kg of ethanol per kg of LCB we are getting. So the last part of the this week's are the transesterification. So this covered about the basic content as what is transesterification, organic waste for transesterification, production of bio-oil from oil seed and major composition, need of upgradation of bio-oil to biodiesel, biodiesel properties, upgradation flowsheet, steps for upgradation, biodiesel production from mixed waste plant oil, grease, combustion of bio-oil, biodiesel in diesel engine. We will check the questions. If you have any doubt of any slide, you can get back to me. So during the transesterification process, alcohol such as methanol reacts with the dash to form fatty acid alkyl esters, which is known as biodiesel and glycerin. Options are triglyceride oils, So the first question is, again I'm taking the questions quickly. The maximum theoretical ethanol yield can be calculated by Y max percentage equals to ethanol produced reactor by initial sugar in reactor into 0.511 into 100, or it's 511, or it's 3.511, or 5.511. Correct answer is 0.511. Ethanol produced in reactor divided by initial sugar in reactor into 0.511 into 100. Biological route uses dash bacteria for the production of ethanol from lignocellulosic biomass. Correct answer is Clostridium jungdali. Biological route uses this bacteria Clostridium jungdali for the ethanol production from lignocellulosic biomass. Then this numerical problem. In a high-rate biogas plant, food waste is anaerobically digested to produce biogas. The slurry contains 8% of solid food grains. Elemental composition of the food grains is carbon 58%, hydrogen 8%, oxygen 26%, nitrogen 8%. 80% of food grains converted to biogas, and all the converted hydrogen forms methane. Slurry flow rate given 4500 liter per day. Calculate the rate of biogas CO2 plus methane production. So we had discussed, if no screen share was not there, I don't know. Might be some technical glitch. You can pause the recorded video here and check the solution. I have discussed this verbally. During pretreatment, 50% of the mass of a lignocellulosic waste is converted to monosaccharide and disaccharide. In mass ratio of 6:4, monosaccharides produce 510 gram ethanol per kg of monosaccharide, and disaccharide produce 540 gram of ethanol per kg of disaccharide. Assuming same mole ratio of both monosaccharide and disaccharide as 1:1, calculate the yield of ethanol. Again, this was also discussed. So if the screen share was not on, just pause the video and check. Very important two problems, might be helpful for your examination as well. Okay, and then came to the first question of transesterification. During the transesterification process, alcohol such as methanol reacts with the dash to form fatty acid, alkyl ester, and glycerin. Triglyceride oils contained in plant oils, animal fats, recycled greases, or all of the above. So the correct answer is all of the above. During the process of transesterification, an alcohol such as methanol reacts with the triglyceride oils contained in plant oils, animal fats, and recycled greases to form fatty acid alkyl esters, which is nothing but biodiesel and glycerin. The conversion of free fatty acids (FFAs) can be determined from the following equation. S naught is the initial acid value, Si is the acid value at some reaction time. Okay, these are the formulas which is the correct one you have to take. So the correct answer is the percentage conversion equals to S naught minus Si by S naught. S naught is the initial acid value and Si is the acid value at the some reaction time. Basic formula of conversion, nothing else. The acid value is calculated as 56.1 into V into C divided by M, 56.1 into V divided by M into C, 56.1 into V divided by C into M, 56.1 divided by V into C into M. Correct answer is 56.1 into V into C divided by M. The acid value, so S is the acid value in milligrams of KOH divided by grams of WCO, waste cooking oil. C is the concentration of the KOH used for titration in moles per liter. Capital V is the volume of KOH employed for titration in milliliter ml. M is the mass of the sample taken to be analyzed in grams. Correct answer is 56.1 into V into C divided by M. In transesterification process, the plant oil, which contains less than dash percentage of free fatty acids, is first filtered and then pre-processed to remove water and other contaminants. 4, 10, 15, 20. Correct answer is 4. And the plant oil, which contains less than 4% free fatty acids, is first filtered and then pre-treated, pre-processed to remove water and other contaminants. Select the factors which affect the performance of transesterification process. Reaction temperature, time, free fatty acid content, all of the above. The correct answer is all of the above. So the factors which affect the transesterification process are reaction temperature, time, free fatty acid content, catalyst type, alcohol to oil mole ratio, catalyst concentration, mixing, water content, types of alcohol, catalyst types. So all of these are important factors for the transesterification process performance. Today's last question. You have to match the following feedstocks with the catalyst used for the production of biodiesel: sunflower oil, soybean oil, babassu coconut oil. With the catalyst potassium chromate, potassium carbonate TiO2, embellished 15, is sulfonated ion exchange resin, and strontium oxide SRO. So you can check this particular table. So sunflower oil is used the strontium oxide as the catalyst. For soybean oil, it's the potassium carbonate and TiO2. Titanium and potassium will be ratio 0.65 is to 1, and coconut oil is the embellished 15. This is one sulfonated ion exchange resin. So this will be the correct answer. 1R. Sunflower oil will be strontium oxide. Soybean oil would be potassium carbonate TiO2P, and coconut oil is the embellished 50. That's all from today from my side. Thank you.
Hello, sir. Am I audible?
Yes.
Sir, I just wanted to know about the examination pattern, like what sort of question can be asked in the exam. Like you are giving a lot very informative slides. Those slides are having bulk of information. So constituting that 8 week course, that slides are getting like 1,000 plus slides are there. So how to categorize that? What sort of questions can be asked in the exam from that slide? Like all the slides are, I believe I'm learning all those deeply, and all are equally important, so it will be nearly tough to remember all 1,000 plus slides. So what sort of
I
exam
think
questions
you can focus on the some of the numericals and also
okay,
this kind of MCQ type of things which are discussed. I understand because it's more of
yes
a
sir,
very much theoretical kind of things are there.
yes sir, yes sir.
Yes,
So
I
that
understand.
that is why it is
Hmm.
nearly impossible to remember all those things,
Hmm.
and all on
So,
different kind of datas are there na. So
so
I
I
was
what as by my understanding,
yes sir,
the questions should be a bit of conceptual, not based
okay,
on data oriented, which you have to memorize. So
okay,
it's to assess how you have understood the subject, understood the course, understood the
yes sir.
concepts. So I think that from that point of view, you need to check the slides and all.
No, sir, from
So
that point of view, I'm learning the
hmm,
things, but it is getting
I
since it's
understand.
a
Like even in
yes, sir.
our example questions, there are a lot of
Yes,
kind of
sir.
theoretical questions are there. I understand. What is the name
Yes,
of enzyme or something, something, this
yes,
kind
sir.
of
Yes,
thing.
sir.
So
Mm,
These things might, I am obviously I cannot like tell you what exact questions will be there, even I don't know. So, but
okay.
as by my understanding, the things are like you have to use your head, and so maybe there will be 10-15% of this kind of memorizing question. Maybe there will be. So, but I think major focus might be on the this thing, conceptual things. You
Okay,
can
sir.
ask them also, like we don't have this knowledge actually about the
Yes, sir.
examination. So you can
Okay.
also ask the team of this particular course, right? There is also an
Yes, sir.
forum or something like that, na?
Yes, sir. The
Hmm.
forum for question and answer is there.
Yeah, yeah.
My doubt was like that. Suppose I'm doing currently with I'm learning the things from the lecture and I'm doing the assignment. But for the compilation of totaling 8 weeks, there are suppose 1,000 plus slides are there, and it is very informative kind of slide. The each
Hmm.
slide is having bulk of
So
information.
you majorly, like I would suggest to don't miss out the numerical problems in the
Yeah.
the slides. So
Okay.
that will fetch you the marks directly if you
Yes, sir.
can do it correctly, right?
Yes, sir.
So for the numerical
So
thing, you need not to
similar
memorize
sort of
anything.
questions will be there, sir, or
Hmm.
some sort of change will
Sorry,
be there. Similar sort of questions will be there
I think
in
so. Yeah,
exam.
yeah, yeah, yeah.
Okay.
If you have gone through these things, I think
Yes,
this
sir.
this would be like sufficient, more than sufficient usually.
No, in some
Again,
numericals, no, sir, and
mm-hmm.
they are like a bit big numerical. In that case, you have to remember moles, molecules,
No,
and
no,
you
no,
have to
no. I don't
derive
think
each and
you have to remember things for numericals also. Just basic, like they would not give you the molecular weight of CO2. So you know that thing, right? Assuming that.
yes, sir.
But that's a very basic thing. But if you have, like, there are certain correlations are there, right? Like those
Yes, sir.
using volatile matter, like proximate analysis, there is some
Yes, sir. Yes, sir.
different
Yes, sir.
scientists are giving them different, composition, those
Yes,
carbon
sir.
percent and etc. etc. So those
Yes, sir.
correlations, I don't think that will be much helpful also for you to memorize. These are basically different scientists has performed some experiments or some theoretical
Yes, sir.
calculations and got those kind of results. Okay, so
Yes, sir.
don't memorize useless things. Focus on the important concepts. So ultimately, the purpose is to learn. So that
Yes,
is
sir.
the thing, and that is, I think, would be good for you.
Okay, sir.
Okay.
Okay, sir. Thank you. Thanks a lot, sir.